Fibonacci number, Leet code question 509. The Fibonacci numbers, commonly denoted as f of n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones starting from 0 and 1. So f of 0 is equal to 0, f of 1 is equal to 1. Otherwise, f of n, so any other number besides 0 and 1, or a positive number besides 0 and 1 is the sum of its preceding, so of its preceding f. So if this is like 10, then this would be f of 9 and f of 8. And then they have some examples here, what f of 2 is, what f of 3 is, and what f of 4 is. So when I think of something, when I see this, the first thing I immediately think of is a recursive function, because let's say this is a function. This is calling the function just with a -1 argument and a -2 argument. So what do we know here? We know that f of 0 is equal to 0 and f of 1 is equal to 1. So that's what we know. We also know that if f, or if n is bigger than 1, then f of n is going to be equal to f of n minus 1 plus f of n minus 2. Okay, so this is what we do know. In recursive functions, we need an end condition. So, end condition. What is our end condition? Well, our end condition is the only thing we know, which is when n is equal to 0 or n is equal to 1, then end the recursive function is called. So that's pretty much all we need to know to solve this equation, actually, or solve this problem. Fib solve n, which is ins s is equal to solution s dot fib. Let's do a number that we haven't seen, so fib of 5. Okay, so if we start writing this out as a recursive function, we could say if n is bigger than 1, then return itself n minus 1 plus self dot fib n minus 2. So that's the first thing that we can know, that we know, is that if n is bigger than 1, then the Fibonacci number is going to be fib n minus 1 and then fib n minus 2. And when you do recursive functions, you need these arguments that continuously decrease itself by a certain number, because if we didn't have this, then fib would continuously call itself forever, infinitely. So minus 1, minus 2. And right now it still continuously calls itself infinitely as well, because n will continuously decrease into the negative numbers. So we need an end condition to tell us that the recursive function is ending. So what will our end condition be? Well, our end condition is if n is equal to 0, then we just return 0, because f of 0 is equal to 0. And if n is equal to 1, then we return 1. So this is our end condition. So let's just walk through this. So right now we have s dot fib 5. So is 5 equal to 0? Is 5 equal to 1? This is what this is calling. Is 5 equal to 0 or is 5 equal to 1? No, it's not. 5 is bigger than 1. So therefore we call itself again, but with with a detracted argument. So now we're going to call self.fib4 plus self.fib3, and that makes sense because self.fib5 or fib5 is going to equal to fib4, that's a 3, fib4 plus fib3. So that makes sense because that's a Fibonacci number. So is 4 0 or 1? No, but 4 is bigger than 1, and 3 is also bigger than 1. So we have to call it again. So what is self.fib4? So we know self.fib4 is just fib3 plus fib2. And then, so that's what this is calling, fib3 plus fib2. And then fib3 is just fib2 plus fib1. And then we just continue going down. So fib3 is fib2 plus fib1. And then fib2 is fib1 plus fib0. And then fib2 is also plus fib1 plus fib0. And then fib1 is just 1. Because fib1 is, we returned 1 here. Okay, so now let's just refactor this. So for a recursive function, we went down the stack, down, until we reach the end condition. So this has the end condition. So what are we gonna do? We're gonna continuously go up now. Actually, no, we haven't reached the end. We haven't reached the end. We still have this guy. So actually, yeah, no, we can do it like this. So a recursive function goes all the way to the end, and then after that, once it reaches the end conditions, it'll go back up the stack. So right now we're down the levels. We're 1, 2 down levels. So fib0 we know is 0, fib1 is 1, fib0 is 0, fib1 is 1, fib1 is also 1, and then we have fib2. So what is fib2? So fib2 is fib1 plus fib0. Oops. And fib1 plus fib0 is just 0 plus 1. So fib2 is going to be 1. Okay. So now fib3 evaluates as 2 because of these two numbers. Fib2 evaluates as 1 because of these two numbers. Fib2 evaluates as 1 again because of these two. And fib1 was just fib1 to begin with. So there's that. Then fib4 now evaluates to 3 because of these two numbers. And fib3 evaluates to 2 for this, so that at the end of the day, fib5 is 5. Fib5 is 5. So let's see if that's correct. So p test.py, and we didn't print it out, so let's print it out. So fib5 is 5. That's crazy. So let's see if it works with the other numbers. Fib10, and I'm not going to go through all of that for fib10, but that should be 55. So that's correct. Okay, so let's walk through what a recursive function is again, but with pictures. Well, with my ugly drawings. So let's say that we have 5 stacks. So 1, 2, 3, 4, and 5. And let's pretend that these rectangles are exactly the same height and same width. I know it doesn't look like that in this photo, but let's say it does. Okay. So this is, let's say this is 5. So this 5 is going to check a condition. So this 5 is going to check a condition. Is 5 the condition? No, the 5 isn't the condition. So let's call itself again. Calls itself again, but it calls itself with a -1. It calls itself with a -1. So now this is a 4. Is the 4 this is the condition? No. let's say the condition is that it has to be 0. So is 4 the condition? No. So then it's going to call itself again. So that's with a 3 with a -1, 2 -1, and okay, you know what? Let's for simplicity's sake, let's say the condition is 1. So keeps on calling itself, continuously calls itself with a -1. That's what our n-1 was. So continuously call itself n-1. It'll check again. Is our condition? Yes. So this is our condition. So now it's going to go back up. So whatever this 1 evaluated to, it'll return whatever the end condition evaluates. So let's say if the condition was 1, then we'll return a 1. So now we return this 1. So now this 1 will return 1 to this 2, and this 2 is going to take that 1. You can do whatever you want with that 1, and then after that it'll take that and it'll return back up, return back up, return back up, and then whatever it returns, whatever it continuously returns, our end result is going to be up here again. So our end result doesn't end here. Our end result goes back up to the very beginning. So that's what a recursive function is. And so yeah, this is the solution to Fibonacci numbers, Leet code number 509.